This is the second video in the geometric sequences videos. And the last one we ended with this sum formula right here, this sum statement. We were going to get the sum of these terms when k is 5 to k is 15. And we used this formula right here. The sum equals the first term times 1 minus your common ratio to the number of terms that you have over 1 minus your common ratio. So we're going to use that formula. I'll just go through that real quickly again. So the sum equals, now the first term is when k is its beginning number, okay, its lower limit. And so the first term is when k is 5, so 3 to the 5th, and then 1 minus, and the common ratio is 3 in this case. And then we talked about the fact that how many terms do we have? Well, 15 minus 5 is 10, so there are 10 numbers between 5 and 15, but you also have to count the first number, so that's 11 terms. So we have 11 terms, and then 1 minus 3 on the bottom. And when you calculate that out, and we'll just do it really fast here, this ends up being 48.6. And this is 1 minus 177, 147. Now that's going to be, check my number there, yeah, that's going to be a negative number. That's a negative number. So the negatives go away, and so they become positive. So when you get your final sum here, 48.6, and then times 177, and then divided by 2, we get 4304647.8. So 4,304,647.8. The numbers are increasing in size, and so the sum gets to be pretty large for just 10 terms. Okay, so now this one is an infinite sum. Can we do an infinite sum? Well, let's think about it. So we have an infinite number of terms, and our common ratio is 3. That means the numbers are continually getting larger. Well, an infinite list of those then is going to be infinity. And so the sum for this is infinity. We don't even need a formula. This guy is an infinite sum, but my common ratio is 0.2. That means it's a number less than 1. That means that all of my terms are decreasing and they're heading towards 0. That those terms then towards the end of the sum aren't really going to affect the sum. And so we have a formula for that, and it's A1, the first term, over 1 minus your common ratio. So we're going to use that formula for this infinite series because, and you can only use this one for an infinite series when your common ratio is less than 1. So my first term, of course, is when k is 5. So we've got 3 times 0.2 to the 5th over 1 minus, my r in this case is 0.2. All right, well, 2 to the 5th is 32, but we're going to have to move the decimal over 5 places, and then multiply that by 3. And so, and we're going to get 0.00096 over 0.8, and when I do that math, because 1 minus 0.2 is 0.8, then I get 0.0012, and that's the sum of that infinite series. Now we're going to use this formula, the sum of an infinite series, to write a repeating decimal as a fraction. So here's an example. Let's say we have the repeating decimal 0.777 and so on. I can rewrite that as 0.7 plus 0.07. So I'm just going to separate each one of these 7s out. Plus 0.007. You see, if I line up my decimals and I add all of these up, I'm going to get a series of 7s. And it goes on and on and on. So my first term, and I'm going to write these as fractions, my first term is 7/10. My second term is 7 over 100. My third term is 7 over 1,000. My fourth term is 7 over 10,000. It just goes on and on. Well, I can rewrite each one of these using the term in front of it. So this is my first term. So my second term I can rewrite as this term in front of it, 7/10, times 1 over 10. I just need an extra 10 in the denominator. And I can do the same thing for this guy. This guy, 7 over 1,000, is the same thing as 7 over 100 times 1 over 10. I just need an extra 10. And this guy, same thing. I can write as 7 over 1,000, and then that 1,000 needs an extra 10 to become 10,000, and so on. So each time I'm writing my next term using the term in front of it, and then I'm multiplying by the same number each time. So that means that I can see this as a geometric sequence where A1 is 7/10, and the number I'm multiplying by to get the next number each time is 1/10. So my sum then becomes A1, which is 7 over 10, over, see, A1, over 1 minus R, 1 minus 1/10. And so this is 7 over 10, 9 over 10. The 10s go away, and you get 7/9. And that's what the repeating decimal 0.777 is as a fraction. Let's do that again. Let's suppose we have the number 4 and then a repeating set of 13s. Okay, 4 and 1, 3, 1, 3, 1, 3, 1, 3. Okay. Now the 4 is just kind of sitting there on the outside. So we're not going to do anything with him except we don't want to forget it. Now, this is 0.13 plus, and then the next 13 is going to be 0. And I'll have 2 zeros in front of it. And then the next 13 has 4 zeros in front of it. And it keeps going that way. All right? So 4 sitting on the outside. This is 13 over 100. This one is 13 over 4 zeros. 1, 2, 3, 4. Okay, 10,000. The next one has 13 over 6 zeros. So that's 1 million. You just keep going. All right, well, my geometric sequence is going to be the series of 13s. And so my first term, 13 over 100. The next term I'm going to write as 13 over 100, my term beside it. But then what do I have to multiply 100 by right here to get 10,000? Well, I have to multiply by another 100. And then the next term I can write as 13 over 10,000. But I have to multiply by 2 more zeros, 1 over 100. And each time it's going to be that way. I can write this number as by using the number in front of it and multiplying by the same number every time. So here's my A1, my first term in that sequence, and then I'm multiplying by 1 over 100 each time. So the sum of this part of my number is going to be A1, 13 over 100, over 1 minus R, which is 1 over 100, and that's 13 over 100 over 99 over 100, so that's 13 over 99. Now, I need to add the 4 to that. This was just the sum of that sequence. So my real number is 4 and 13 over 99. That's what a mixed number is. When you've got a mixed number, you're adding a whole number in a fraction. All right, let's do one more. Let's do one more. Let's do the number 0.1666, so on. All right, so when I rewrite this 0.1 is just kind of a spectator. He's a spectator part of the problem. And then the 6's, I've got 0.06, plus 0.006, so 0, 0 for the 2 places in front of it, plus 0.0006, and so forth. 406, and it just keeps going. Okay, well, here's my spectator point 1. Now, this is 6 over 100. This is 6 over 1,000. And then we have 6 over 10,000. And then we have 6 over 100,000. Well, each one of these can be written as the number in front. So my first number, 6 over 100. Here's my second number, 6 over 100. The first number times, all I have to multiply by is another 10, so 1/10. And then my next one is 6 over 1,000. And all I have to multiply by is 1/10 to make it 10,000. And then the next one, 6 over 10,000. And I just multiply by 1 over 10 to make it 100,000. So you can see that my A1, my first term is 6 over 100. My R is 1 over 10. So when I do the sum of this repeating decimal part, I have 6 over 100, 1 minus 1 over 10, okay, 1 minus R. Well, this is 6 over 100 and then 9/10, but that's the same thing as 6 over 100 over 90 hundredths. And that's going to, the hundreds are going to go away, okay? And I'm just going to have 6 over 90. Well, 3 goes into 6 2 times and into 90 30 times. So that's 2 over 30, which is really just 1 over 15. Now, can we see that? Yes, we can. 1 over 15. So I'm going to take that 1 over 15 because that's the sum of the repeating decimal part. But remember, I've got this 0.1 I've got to add to that. Well, 0.1 is 1/10. So 1/10 plus my 1 over 15. All right? Well, this is 3 over 30 plus 2 over 30 equals 5 over 30, which equals 1/6. So that repeating decimal is equal to 1/6.